and then we'll make this more correct anyways. Well, no, we actually wrote our original code correctly, yeah. We're already updating program counters everywhere where we're supposed to be updating program counters. I made a poor assumption. Well, where's my begin down here? I said, oh, I'm going to write directly to memory, right? Mm-hmm. Assuming that won't update program counter. Exactly. But it does, because we update program counter at the set to list value helper level. So at the very core of all of those loads and stores is this top level thing for that helper, and that updates the program counter, which makes sense. Whenever you're updating a to list, we just moved past an instruction. So we mistakenly said, oh, that doesn't change the program counter. This must not change the program counter. And then we had an SW thing here thinking, oh, well, that's the guy that actually changes they all change the program counter. So you just subtract 2 from it. Now your program counter is 1 forward of what it was before. Okay. But I'm actually, I put the set bang thing, but I'm going to change it again anyways. Because this actually is not an accurate representation of how this would really work in assembly. The book did maybe a crappy job of explaining that because the example they gave started it off as a 1. But let me show you how this would actually work in assembly. Here, I'll just show you this one here real quick first. I run it. All we have is our input function. I put a 4 there. We should have an 8196 or a 4 and 8196. Yep. Okay, and 8192 should be back to a 0, but I just copied the line. So now it does exactly what it's supposed to do in terms of the end. All right, so there's my 8196. There's my 8192. Now, the way this would actually work on a CPU, I would never actually call something like this on a CPU. You don't actually tell a CPU to do an input like this. The input would happen underneath the hood. So when does a CPU go into input mode? Whenever we put a 0 or whenever we put a 1 into 8192. So we would do something like this. We would say add I, what's it, 0? Actually, we need to put into a destination register. So we'll say T0. Zero, 1 like that. So T0 currently holds the number 1. Correct?
Then T0 should also have the single quote.
Is that how this works?
I don't know.
No, because this is a list of.
Otherwise, 0 don't.
Yeah, this is correct because the whole list is quoted. Yeah. So we put a 1 into T0. That's what we're doing here. Then what I would do is I would store. Store into I would store the value of T0 into 8192.
Now it should hit input.
Okay, correct. That should now fire input. Mm-hmm. When I store when I store a 1 into 8192. So this is going to be similar to that output thing. So now if I go, and then what we would do is I would read input, and it would ultimately put my value into 8196. So I would then load word T1 8196. And now T1 should hold whatever we read in. Okay? Well, let me just say that one more time. No, this is how it would really work.
This is how it would work, but is this how it is working right now? Or
it's how it's going to work in about 4 minutes.
Okay, that's what
yeah. Okay, so it's going to be just as simple as the original one we did for the output. The input's going to work the same way. We're just going to be doing it in the other function. So add I. So this puts a 1 into T0 because I'm going to need a 1 in order to put it into 8192. What does 1 mean? 1 means says I want to do input next. So I get a 1 and then I put a 1 in 8192. I want to do input next. As soon as we store this number 1 into 8192, our CPU goes into input mode. Okay, it goes into I/O mode. I'm actually going to show you a programming example of this in a second where we're actually going to see the sluggishness of it because our CPU actually gets interrupted to do I/O. All right, so we're going to put this guy into I/O mode. So we're going to notice in the implementation of SW that, oh, you're putting something into 8192. That could be problematic. Specifically, you put a number 1 in there. That means the next thing you want to do is input. So after this line, our CPU actually pauses. It gets blocked to do input. And when input is done, then I can grab into T1 whatever we just magically found in 8196, which is where input puts its input. That make sense? What was your question, Blade?
My question is, since it is the CPU doing the input, why it's being saved into memory rather than directly into register?
It wouldn't be the CPU doing the input. The CPU would actually rely on the operating system to do the actual input. If you remember when we looked at the Hello World program in Linux, it's done in terms of the operating systems and the system calls. So we would probably do like a sysin or something like that. You'd probably use the underlying operating system of the OS, which would then know that this particular architecture for the CPU requires that 8192 does the interrupt. 8196 then goes and, so what would happen is sysread is probably the name of the system call for Linux, would check. He actually wouldn't care about 8192. The CPU would care about 8192 and notice, you want to stop and do input. Who does input? The operating system does input. So sysread for that architecture, so this would be the sysread for the MIPS architecture from the Linux operating system, let's say, he'll go and do whatever magic needs to happen to read something in from the user. And then ultimately he will store that in a very, very specific place, 8196. And then he'll turn it back over to the CPU who knows to check that very specific place.
So actually, in between, technically, this is not really CPU reading anything. This is OS doing something, but it's saving a specific place. CPU knows where it would be.
Right. The CPU can't do I/O on its own, but he knows how to tell himself the programmer, us, that two-line punch there, that effectively says CPU stop. The OS is going to do something.
Okay, I see.
And realistically, the CPU would know under the hood to call the specific input instruction, the sys input for that architecture. We're kind of leaving we don't have the OS side of this represented. So we're playing the role of the OS by using scheme's input function, right? So he'll go and do that. And when he comes back, he will put the thing he read into the secret memory location that only everybody, including the MIPS architecture, knows, and we all know now, that's where you can find the value we loaded. All right, so inside of SW, we need to ask the question, are you storing something in that memory address? If so, is it a 1? Because 1 is what means something to us. So if I go to SW, here's our register name. We don't care about that. We care about the memory location though, right? So pretty similar to what we did to LW. We're going to ask a question here. If equals mem location, and actually, didn't we have to do this for... Yeah, we're not changing the memory location here, so we're okay. We don't have to resolve this. This will definitely be a number. So if mem location is equal to 3192, if that's true, and now we need to get our reg value. So if we want to do this as a, well, here. I'm going to be redundant here for a second.
What are these 3190 coming from?
Oh, it's 8192, right?
Okay.
That's my special memory address, 8192.
Your memory is weird. How you can
All right.
memorize 3
Yeah. Yeah, 8192. So if we're looking at memory address 8192 and the value we're working with is equal to 1, the value we're storing there is equal to 1. If that's the case, we will go ahead and do the store. So let me make sure this closes where it's supposed to. Yep. So we'll go ahead and we'll do the store, but we're gonna do it again. We're gonna do it again. We'll do the store, then we'll actually do our input, and our input is going to see. Actually, would we do the store? Do we actually do the store in this implementation? We're trying to write it to 8192, but do we actually have to do the writing?
No, we don't really.
So if we're trying to write it to 8192, and it's a 1, we do our input.
Yeah.
And we're going to put our input at, we're going to do a store at 8196, SW, what value, whatever's returned by input, into 8196. So that's what we'll do in the event that we were trying to put a 1 into 8192. Okay, so if that's true, do this. Else, do this. Whenever we store, what do? Well, we'll start off by making sure this isn't one of our special stores. If we're storing at 8192 and it's a 1, then we actually want to store in 8196 the results of an input. Otherwise, in any other case, if it was 8192 and it wasn't a 1, or if it's any other memory address, we'll just do our normal plain Jane store. That make sense?
Yeah.
So that's what that guy does. We've interjected this special little thing here. So now what we'll do, and it's not input, it's read, isn't it? The scheme function is called read, not input. So then down here, we will take out our function for input here, because that's not a thing. That's not an assembly instruction. Our assembly instruction is to put a 1 into 8192. That flags our CPU for time to do I/O. Then we do IO, and we prove it happened by putting into T1 whatever we found in 8196, which should be the number that we read in. Okay, so first two lines are already fired, right?
Yep.
The first line is, hey, well, let's just put into T0 the number 1. Cool. Then we're going to store a 1 in 8192. That's when that AND fires and says, okay, you don't actually want to do a store. You were giving me the secret signal. The secret signal says do input. So now it's waiting for me to do input. I'll put in a 4. I'll press enter. Now, because we're in the secret signal input thingy, we know that that 4 is actually going to get stored in 8196. And I hope I wrote that up there instead of 8192. Who was in charge of that? Probably Ani. Okay. So I'm going to bring from 8196 into T1, which should be a 4 in T1. So here's my... Where's my T1? Yeah, it's a false. So did I do 8192 again? Oh, there's my read. Do I have it backwards? Oh, no. This is same thing we had to do before. This takes in a register name. Yeah, where we're actually giving it a value. Yeah. So we need to ask the question. We can go ahead and just get the read.
How about just using set DM value?
Oh, directly? Yeah, I guess we could. But not, it wouldn't be set DM value. It would be set, it would be set DM value. And that takes in a value and a register. Actually, it's the other way around, I think. It's a register and then the value.
Reverse.
So we'll just bypass having to resolve this register name since I don't actually have my value stored in a register. I have my value being read in directly from read. And I'll go ahead and put that in memory address 8196. So there's my 4. There's my 4 in 8196.
Okay.
And then my T, what was it, T1?
Yeah. Okay.
T1 is a 4. So that's how I/O would actually happen on the CPU. We need to tell our CPU to enter into input mode. Then we tell our CPU, then our CPU will do input. We don't have to ever use the value if we don't want to, right? I can go on and do some other stuff on my CPU if I really am interested. You know, I can just forget about this in T1 and I could do like add I, T1 14, something like that, whatever. 8196 will still have my value in it. I used add I incorrectly. I probably used add I incorrectly. I did. So it would be T1, T3, 14. Destination, source, immediate. So we see 8196. It has the value we entered in there. I didn't use it, never moved it into a register, potentially wasted my time, but it's there. Make sense? All right, so that's how I/O ultimately will work on our CPU. Now, so we have input and we have output now working. Okay, and that's the end of chapter 2, looks like. So chapter 3. Subroutines. So we're going to allow ourselves to have functions. So now what's a subroutine? Subroutine is an old school name for functions or procedures or methods, right? So what's the definition of a subroutine? Yeah, it's a set of instructions that we write once and can call multiple times, right? All right, so we might have something that maybe does some input. That'd be a little cryptic of every single time we wanted to do input. We had to do those couple of things, right? So maybe we go ahead and we want to write a subroutine. Let's get some sample code here. So we would create a label, and that label would then have the instructions for our stuff. Now, right now we support a does this works just like normal labels? Normal labels have a colon after them as well. We just don't do that in ours, right? I'm pretty sure.
Ours does not return to some point like this one.
Yeah, I'm just looking at a normal label. Yeah, this is just a normal. This is just a normal label.
Normal label will also have
A colon. Okay, so and we're not storing colons with ours. We just have ours as a label. So just to keep life simple, or at least consistent with the way we're doing things now, we're just going to add a little rule into our little world that says that the first line of our instruction, first line of our subroutine, will be on the same line as the label itself. It wouldn't be that hard to change it, but that's how our thing currently works. We assume that that's where it starts, because remember in that else, we peel off the label and then execute the rest. But if the rest is empty, we would then just move on to the next line, which actually wouldn't be hard to write anyways. Because that's just in this else. So this else says, I'm looking at a car that's a label. And what am I doing? I'm calling execute instruction on the footer of that automatically. But what if it was just a label like this one? What if it was just a label and the actual instructions started on the very next line? We probably then don't want to be calling execute instruction on that, right? So we would actually do this. We would say if equal length footer instruction is 0. If there is nothing after the label, that means I'm actually out of stuff. And if I'm out of stuff, that means that my stuff must be on the next line of my program. Yeah, so I need to update my program counter. This guy right here. So if it's equal to 0, then update my program counter. Else, the line must actually be there. So call execute instruction on the rest. Let me just make sure this ends where it's supposed to end. Nope, one short. All right, so if I'm in this else, this means I'm looking at a label, right? That's what this else means. I'm looking at a label. If the stuff after the label is non-existent, if the length of my list after that label, when I take the footer of it, has nothing there, that means I don't actually have my instruction on that same line. What do I do in that case? I update the program counter so that the next time this gets called, it's operating on the next line. Else, my instruction must have been on the same line as the label, so I'll go ahead and execute that instruction. That makes sense? And we could actually test this without doing any more changes to anything, moving on to other things with subroutines, by writing just a simple thing here, something like, we'll just do it with a jump. So we'll say jump my label, like that. And then we'll have our my label, and we'll have my label, and this guy will do a add I of, we'll put into T0, then 0, 5. Then I'll do a jump mylabel 2. And this guy will have a mylabel 2 on it. And the next line will be add I T2 7 or something like that. All right, so this first jump jumps to a label. Here's the label. We're in the else. The cooter of this guy is not a length of 0. Therefore, we should actually put the 5 into T0. Then we increment to the next line. We jump to mylabel 2. We go and find mylabel 2. We're in the else. The cooter of this guy actually does have a length of 0. What do? Increment our program counter. So the next thing we'll do is this guy right here. T2 is going to be 7. So there's my T2 is 7. There's my T0 is 5. So now we support putting code on both the same line as the label or on the next line of the label. Make sense? Okay. So now we can write cool subroutines.
Can you go back to your custom?
Possibly. Ninja.
Did your chair always squeak, or is that new?
That squeak?
No.
That's my shoe.
No, it's like a...
That's my chair. That?
Nope. Your little movement squeak. That's me.
Is it doing it now?
Rock back and forth. Can't get it.
Are you sure? It's got to be my foot. Like, it must just be.
No, it's not.
I'm pretty sure it's your chair too.
Really? Okay. Oh, I just.
Nope. Stop that. I'll let you know.
Everybody stop!
Did you hear that?
All right, do you get what you need from here?
Yeah.
All right, so let's do subroutines. So subroutine is just a label, right, where we have some stuff. But we have this last thing here, this jump return, right? Is that what it stood for? JR's jump return? All right, so what we need to do is when we branch to, so here's like our example here. So when we, JALs, let's say jump to, what does AL stand for? Jump algorithm? What is JAL? Jump and link, okay.
Yeah.
So we do jump and link, and what this is going to do is it's going to remember where we currently are. All right, we need to, because we need to be able to come back. All right, so we need kind of like a temporary global variable to remember where we currently are. And we do this, so we have this register called the jump register, JR, and is that in our list of registers? Where's JR?
It's RA, right? JR is just the...
Oh, the name of the register is RA?
Yeah.
Okay, so we have a new register that we're throwing into the mix here called RA. And we're using this guy as a variable, because that's gonna temporarily hold our program counter. Does that make sense? Mm-hmm. And what's nice about that is, actually, is that something that's nice about it? Maybe not. Doesn't matter, because we're gonna be changing our location anyways. So we need to go up to our registers. And now we're gonna have, what was it, RA? Yeah. And we'll start that off at 0, that's fine. Okay, so that guy is for our return register. Okay, so now we have an instruction called JAL that's going to take us to a label. So let's go ahead and let's write some code here. So we're going to, in fact, well, I don't want to do, so we're going to do this. We're going to say JAL get input, something like that. And then down here, we're going to have a get input. And we can put this wherever we want. Get input is going to do what? We're going to, well, we're always going to use, let's say, T0 for our input for no good reason. So we'll say add I, T0, 0. Oh no, we can do a load. Add immediate. We're going to put the 8500. Then we're, so if I do load word T0, because ultimately if I'm doing input, I need to load something in, I need to load something into 8192.
Yeah.
Okay.
Should,
Gotcha.
W.
So I'm going to do add I, because I can't give it a solid number for SW. So I'm going to do add I T0 0, and then we're going to do SW, and we're going to store to 8192, but the order is T0 to 8192. Like that?
Yeah.
All right. So that's what does input. Correct? And the result of that will be read something in. You will find your answer in 8196.
Yeah.
We're not reading it from 8196 or anything, but that's what that guy does. So we can do other things in between here, whatever. So I can come here and I can say, load word T1. I can even use T0 again if I want. I could say LWT0, 8196. So then T0 should have in it what I just read in. And then, and a lot of times the functions are up top because we would just run right into the next thing. Well, we'll see how they handle that in a second. So then we'll just do a jump. Done. Yeah, I need to have my JR. Just like that, JR, right? Oh, JR, RA. Yeah. And then here's my done. All right, so this would be a program. So the very first thing I'll do is I'll get input. That branches me down to get input. I load a 1 into T0. I store into 8192 that 1, which causes the CPU to fire input. We read in the input. We jump return back to RA, which should put us back to here, the next instruction. What does this instruction do? We load into T0 whatever we found in 8196, which should be the result of getting input. Then we jump to done, which jumps us past all that, and the program's over.
But hold on, the JR is gonna take back the T0, right? Because it returns the last registered file that worked with.
Isn't RA storing the program counter? Jumps to the instruction at the address held in a register.
It's like the counter.
Jumps to the instruction at the
line number, essentially.
yeah.
Similar to our counter.
Yeah, it's our program counter. So we're keeping a program counter that tells us what's the next line in the program. So you'll see when we implement our JAL, which we're going to do right now. So does everybody understand what I'm advertising this program should do? Read in, move your answer into T0, finish. That's what this program should do. So we're going to go write JAL here. And we'll put that right here. Equal car instruction JAL, like that. So if we're looking at a JAL, what comes after our JAL? It'll be the name of the label. So we need to go and get that label. So this is actually gonna be pretty similar to our jump, right? So we'll call MIPC find label. On that guy, all right? But there is a little difference because now this guy works identically to the jump as we have it right now. But with a JAL, we have this added thing where we need to remember where we currently are. Does that make sense? So I need to do a little bit extra in here. So I need to go ahead, I'm going to do a begin, and I'm going to store into my register, my RA register. So we're going to do set reg value, and this guy takes in the name of a register, RA, and then the value, which will be the current program counter, but plus 1.
Yeah. And the value should be full. Set back the value. The value is you have
Oh, value, like that? All right, so the first thing I'm going to do is I'm going to store into my register named RA whatever the current program counter is plus 1. Because I intend to come back and pick up at the next line from where I am right now. Make sense? I'm going to pick up there later. Then, go ahead.
Is it going to, is program counter going to change with the other instructions?
It will, but it won't matter in a second. So the answer is yes. Program counter will increment by 1 here. But before it increments by 1 here, I'm giving it its current value plus 1 to store inside this register.
Oh.
So initially, just here's the variable equal to this new number.
Okay, because we're setting it to something else, and then
Correct.
Then it won't matter what program counter is.
That's it. Because after this line is executed, the actual program counter has actually changed. Because set reg value ultimately calls that update the 2-pair thing, which does set thing. But on the very next line here, I'm actually going to update the program counter to the location of the label that we're looking for. So I'm changing it dynamically anyways. So I'm going to say, I'm going to remember what the current program counter is plus 1. So I know where to pick up. That happens before we change program counter. Now program counter actually changes, and then I change it to something else. I change it to the location of where that label was found. Okay, so that's what's happening right here. So this guy says, update program counter to the location where this label was found. And that's the end of my begin there for JAL. My end of my begin. Yeah, it's accurate. Question. Kayaking?
What?
Kayaking? Is that an inside joke or was that on Slack? I don't remember. Was it?
Actually, I might have texted you it.
She had sent me some thing about like the difference between like a 100 level professor and a 500 level professor. You know, like a 100 level, like a student's like in this 100 level class, and you know, saying, oh, you know, the teacher's like so serious. We already have 3 tests, and you know, just all this crazy stuff. You know, do you have it?
Yeah.
Okay, you read it.
100 level course prop. Attendance is mandatory. No phones allowed. 12 hours of homework per week. Also, we have 5 exams and 1 is in 9 days. 500 level course professor. I illegally downloaded the textbook. I'll send you the link. Text me if you need anything. Do you guys want to go kayaking?
And then she messages me and says, is that you? So now, like, I randomly will just like send her just a message that just says kayaking. Sometimes it'll do like a picture or something.
That's so relatable.
In the middle of the presentation.
Yeah, yesterday I sent it to her in the middle of the presentation. She starts giggling.
That's when I lost.
Okay.
That's hilarious.
All right, so that's our
Question.
which part?
Are we gonna talk about the presentation?
Eventually.
Okay.
All right, so this should be the end of JAL. Remember our program counter, move to where we need to go. That's what that guy does. All right, so then now we need to, that's going to take us down here. We're at that label now. We continue on. We're going to do this. We're going to do this, but now we need to write the command for JR. Okay. What does JR do? JR is going to update our program counter, but this is going to get a little dicey. Because, well, here, let's just start writing it and then you'll see why it gets dicey. We got too many people changing program counter in this guy. So, EQ, car instruction, JR, that's the name of it? Then what are we going to do? So if we're JR, effectively what we want to do is we want to update program counter to be equal to whatever is inside of RA, my register RA. Okay, so set bang program counter to, this actually won't be a big deal.
Get reg value.
Yeah.
It's get, it's not set.
Yeah, get reg value. RA. And actually, hold on, it's not, RA just happens to be where I stored it, right?
Yeah, it should be code or the
Well, hold on. So, because this thing, JR took in the name of a register.
It's gonna be T1 in that case because it's the last. It returns the last register value that was calculated.
Well, no, the way this works is it looks like we have a 0 register, we have a bunch of T registers, and then we have this R register. And the R register's purpose is to, is to give us where we left off. So the implementation here would be that JAL should be, it's the return address register. So JAL is implemented in terms of that RA register. So this JAL should set the RA register, which ours did. We set that register equal to the program counter plus 1. Now, if we're looking at a JR, we're going to update our program counter to get reg value. But we are saying technically JR here allows you to give it a register name. So we can actually hijack this. Now, this is good. If you use JAL in conjunction with JR, with an RA, everything will work peachy. All right, because if you use JAL, it will automatically store inside of RA where you should pick up when you come back. Then, if you use JR and you happen to then use your return address there, it'll take you right back where you left off, keep cooking, right? But we can optionally pass JR a different place to go. We can hard code or put a different, load something into a different register and say, hey, just go back to line 3, just cause. That gives you some flexibility to maybe do some like weird loopy stuff and things like that. So the intended use is JAL sets RA. JR should pretty commonly use RA to bounce back to where JAL set it. But we don't actually have to. We can go someplace else and then ultimately jump to some other place. We don't have to use RA. So what this means here is I can't necessarily assume that it's RA here. I need to get the catter of instruction.
Does it also mean if JR there's no register there, it's an illegal statement?
Yeah. But we're not doing error checking at this point on how our...
In this case, it means it must have a register.
Mm-hmm.
In order
Yeah.
That,
Is that how the book say it was optional?
It doesn't say it's optional.
If the register in conjunction with the JR instruction is optional, or does JR always take a register?
I think it
Jumps
always-
to the instruction
It
at the
says
address
jump to
held in
that
the register.
instruction.
Yeah.
after the address.
So JR requires a single input, which is a register. Pretty commonly, that register would be RA if you're using it complementary to JAL.
But it doesn't require to be RA.
Correct, but it does require to have a register. So that means that this guy here is a thing.
Always jump.
Yeah, that's a thing. The catter of instruction will end up being something when we're in a JR. So I'm going to set my program counter equal to the value of CADR of that instruction. And that will update program counter to something else. Which actually, I think that's the guy that would give me a void. I think that'll give me an output of a void. Well, if we do, then we'll do that whole list car false thing, but we'll see how that works. So this guy should then reset our program counter back to where it used to be, allowing us to pick up where we left off. All right, so that's all JR should do. So our program down here says jump to get input. We'll jump down here. We'll hit our else and says, just increment program counter because you don't have any code in that same line. We'll put a 1 into C0. We'll store an 8192 that 1, which will trigger input. We'll read something in. Then we'll jump a JR to whatever's in RA, which should take us right back to here, the program counter plus 1 from where we originally were, which is going to load into T0 the value that is in 8196, which presumably should be the value we read in. Then we do a jump to the done label, which takes us to the end of the program. So if this guy works, we have a subroutine for doing input that will trigger reading something in, store the result in 8196, and ultimately put that into register T0.
Can you go back to JR?
Yeah, I was gonna say, do you just close it off?
I don't know.
Do you just need to set it? And then
Oh, hold on,
keep
look
going?
at. I didn't have an extra parenthesis there. Let's just run this real quick. So it fired my procedure. There's my, well, here, I'll make it an 8. This we mix it up a little bit. So T0 should be an 8. Yep, T0 is an 8. So this code worked. All right, so you want me to go to JR?
Mm-hmm.
This is what JR does, right there.
So it's just setting something.
Yeah, it resets program counter to the value we previously remembered. Because that's what our CPU does. CPU eats the next instruction according to what instruction program counter tells it to do. Oh.
Guess we're gonna need another break.
All right, does that make sense?
This is vacation. Back to
All right, so that's JR. So now we have, I guess we support subroutines now, right?
Yeah.
Some? I think I could write any subroutine I want.
Not broken, so that's good.
Huh? Yeah, so we
Bring it home broken.
we have all these. We have all that. That works. So we have a JAL. We have a JR.
There's probably a lot more in there.
Is it able to support the labels inside subroutine now?
Labels inside of a subroutine? Well, probably.
Right.
Well,
Because label subroutine are also like the program counting by.
well, but oh, right. It'll support a label inside of a subroutine, but it wouldn't support a subroutine inside of a subroutine.
Okay.
But I'm guessing that How many of you followed that? So, all right. So
Repeat back what you said now.
it will currently support this. So here's my get input. This is a subroutine, right? So I can do, just for no good reason, we'll just call this guy next line. And then in here, I will jump next line. Just cause. It's kind of like doing a little skip in the middle of your subroutine. So we're doing get input. We'll go ahead and load the 1 into T0. Then we skip to this line, which then just takes us to this line. But we are technically jumping to a label. Okay? It's a question.
You're changing program counter too many times and not going back to the correct line.
But this is okay. This works.
But not if you did a different
Yeah.
JAL.
Correct. Yeah, I can't put a JAL inside of a subroutine. Well, actually, I probably could,
You just have to store it in
but
your-
I'm not getting home.
Yeah.
Because as soon as I use a JAL, I'm breaking my old RA.
You lost the original home.
Yeah.
Can't
Well,
you store it in a-
yeah. Good thinking. You don't have to use RA.
That's how we wrote it.
So we have to jump someplace else.
Yeah.
So it does work, right?
Make a VA.
Well, no, you can just put it in T4 or something.
I know, but
Yeah. Well, so let's see this work first, and then let's actually do this example. Because technically, we do, a little bit ago, I talked about how because JR allows us to tell it the name of the register we're jumping back to, that we technically can do some hacky stuff,
Yeah.
right?
If we know what we're
Right.
doing.
So what I'm going to do here then, but we also know that JAL always updates RA. That's what he does. We need to remember that as the programmer. Okay, but we're not going to do a second JAL yet. So this code right now jumps to get input. So here's our subroutine. This guy does a single add, then he just randomly jumps to the next line, which is a label here called next line, which has no instructions on it. So we just go to even the next line. And we store T08192, which fires the input. Then we jump back to RA. Okay, this should work just fine. We're just doing a little hop, skip, and a jump inside of the thing, proving that our jumps to labels still work. All right, so our I made it a 7 somewhere. Yeah, T0 is 7. All right, so that guy works. Nothing special, just labels in there. Labels still work. We didn't break labels when we wrote JAL because a label is different than a subroutine because labels do not involve JRs. I could treat one like a JR. I could build my own JAL without actually using JAL. So like if I come into my code here, instead of using JAL here, I don't have direct access to my program counter here, so I really can't.
Can I ask you just to, so you entered 7 there.
Yes.
Can you just read 7 through each line? Sorry, I'm a little.
Where do you want me to just walk through it again slowly?
Yeah.
Okay.
So you entered 7 there.
Well, so we start here.
Yeah.
We know what this guy does?
Yeah.
This guy takes me to here.
Correct.
Okay? Then I go to here,
Correct.
and that just puts a 1 into this register.
Correct.
Okay? Then I hit this guy.
Mm-hmm.
All this guy does is takes me to this guy.
Okay.
And then I execute this line. This is in that else where I have no instructions. So now I just go to this line. That line right there is the one that actually triggers the input.
The input, yeah.
Yeah, so this halts my CPU, causes it to delay, triggers my input, and then I typed in a 7.
Okay.
Then it returns to my program. We do a jump return back to whatever's stored inside of RA, which returns us to this line. The position of our program counter +1 when we started the JAL.
Okay, Okay, so that's why the error has that counting. Okay.
Yep.
Okay.
So then we put into T0 whatever we read in. Then we just do a jump to done, which is this label down here at the very end.
Okay, then that's okay.
That make sense?
Yeah.
But now what we can do in here is if we want to, I don't know, do something weird, I guess, we can have another, let's do a, we're going to have a function called do something. And this guy is going to add I T4 0 100. So we'll put a 100 into T4. And then we're going to do JR T2, and you'll see why I do this in a second. All right. So I'm never actually going to hit this line. So I'm not going to call that. Well, no, actually, we don't even need the T2. We could do RA here. Oh, no, we can't. All right. So I'm not going to do this JRRA here because JRRA here will actually jump me back up to right here, right? That's what that guy does. But I actually want to do a JAL to do something. And JAL, so forget that this guy's here for a second. JAL do something is going to update RA. But I want to be able to get back. If I do that, then it's going to take me back to this line right here to pick up where I left off, where I actually want to be back at the top. So what I'll go ahead and do is I'll go ahead and I'll say add storing the result in T2 0 RA. So I'll temporarily store RA inside of T2. Then I'll do my jump. And then when I'm done, I'll bounce back to T2, which will take me back up to here.
Okay.
All right, and this is the useless.
You realize we're not following, right?
Useless.
This is the useless subroutine. So this is a subroutine right here, right? Here's a subroutine. Let's just highlight the individual subroutines. That's one subroutine that I have highlighted.
Yep.
It's called do something. All it does is add the number, puts a 100 in T4. It's a dumb subroutine. That's what he does. So he's a subroutine. But when he's done, JR says, go back to another location. What location am I going to? I'm going to the location that lives inside of T2 for some stupid reason. But now, when we go back and we look at my previous subroutine, this GetInput, this guy right here. Forget about all the jumps and stuff up top. Before I did another JAL, which we know will break the RA register. Because when I do a JAL, he automatically sets the RA register to the value of the current program counter plus 1. So if I do that, I've now lost touch with my ability to get back up to here. So before I do that JAL, I remember the value of RA. So I take the current value of RA, I add it to a 0, and I store it inside of T2 before I break RA. That then allows me to jump to T2, which was the old value of RA, which will be this guy right here.
Isn't that the same thing as just storing it into another location?
Storing one into JAL won't let you store it in another location. JAL overwrites RA. I mean, I am storing it in another location right here. Is that what you're asking?
Yeah, but what we're
You mean down here?
Yeah.
Like, can I say RA right here? I can, but if I say RA right there,
No, I'm saying instead of doing, let's see, because you have.
I got a nice infinite loop there, actually.
Do you have JR twice? That might seem
Here, I just deleted that up there.
a little bit. Do you have JR once?
I have it only once now. I took it out of my,
Temporarily.
yeah, but it actually wouldn't make a difference. I could put it still in here, but we'd skip it. We just wouldn't hit that command. But the second I do this JAL, I change the value of RA.
And it only ever changes RA.
Correct. JAL doesn't give us the option of changing a different register. So if I want to get back to my old RA, I had to put that value someplace else. I put it in T2.
Can't we have that too? Can't we, instead of setting register RA, can't we set it to the,
With JAL?
the catter? Yeah,
Well, we could, but that's not what the instruction set dictates.
instruction.
The MIPS instruction set says JAL works by setting RA.
Okay.
That's what he does.
Gotcha.
But JR allows you to tell it where you want to jump, where you want to return to. So I'm just saying I'm gonna preserve RA in a second variable called T2. Then I'll jump to do something. So that's gonna break RA, but good thing I preserved the value. Then I'll do whatever I'm gonna do. Then I'll return to whatever T2 has in it, which is the old value of RA, which would take me back up here.
So you're doing this because otherwise, go down just a little bit. So if it was the line was JR, RA would return T4. Is that why?
Which line? Which line number are we talking about here?
The
261,
last
262, 263. This guy?
JR.
266?
Yes.
Okay.
So if that was a RA right there, that would return T4.
It would get me to there.
Okay.
Because JAL sets RA to the current program counter plus 1. So if I said JR RA here, it would bounce me back to the current value of RA, which is this line right here. I have an infinite loop now.
Okay.
It'll do this, jump back to this, then this, jump back to this, then this. See how it's working?
Yes. Yes. So, but in assembly, that would return T4, right?
No, this just updates T4 with a 100. That instruction right there adds, I'm not returning a value.
But inside, so what I'm trying to say is like inside a JR, RA, inside a subroutine, whatever that returns the last value that was calculated.
No,
Should be
that's not what JR does. JR is a jump return. So it doesn't return a value. What JR does is it says, take me back to a location held inside this register. So I think you're misinterpreting what JR is supposed to do. JR does not return a value like in a Java function or something. JR takes us back to a location.
so because it says here that
The jump register instruction jumps to the instruction at the address held in a register.
Well, but you said you thought it returned to T4. Tell me why you thought it did that.
because I thought that this RA there would return T4 and go back to the line where the next line after the job.
Okay, and you thought that because this was the line that happened right before it?
Yes.
Okay, yeah, that's not how it works.
Okay.
JR JR sets the program counter to whatever is stored in this.
Okay.
That's what JR does.
So because I don't know, the book maybe has
I think it's
give
pretty
a bad example.
And which one? Well, yeah, I've already seen some bad examples in the book, so that's entirely possible.
So 3.1.5. When you go there,
Oh, it's
the
okay, yeah, I got it. It's not, 3.1.5. Okay, this one?
So go to the last questions and tag the second answer.
This guy?
Yeah. Now read what it says.
So the result of a multiplication is written to T3, which is the final value computed by the subroutine. The JR instruction returns from the subroutine by jumping to the instruction after the JAL that called the subroutine.
Now take a look on that the subroutine that they give it as an example. And I have seen that happen in others too. Maybe was just a coincidence.
Well, whatever got us to here. Oh, is this the subroutine up here that got it to the calc EQ?
Yeah.
Is it up here?
Yeah.
Oh, I don't see it up here. This is called calc EQ. So this guy calculates this equation, blah, blah, blah. Yeah, he's asking you different values, so it's not related to this code up here.
Okay, no, okay,
That
but
did throw me off.
so, but either way, like, why would this be returning only the T3 inside the RA there? So, but I did saw other examples that would make me understand that this JRRA would return the last.
Well, when it says the result of the multiplication is stored in T3, so T3 holds the multiplication of T5, T0, so that's in T3. So the result of the multiplication is written in T3, which is the final value computed by the subroutine. That's what the subroutine does.
Okay, yeah.
It sets T3 equal to the answer.
Yeah.
The JR instruction then returns from the subroutine. Doesn't return an answer. It ends the subroutine, returning us to a previous location.
Okay.
And that location is the instruction after the JAL that called the subroutine, because JAL sets RA.
Okay, so then on this case, let's pretend that on the top we have another add I with T3. The T3 would be whatever its value inside that subroutine, right?
Yeah,
T5 too?
the most recent change to T3 will retain.
Okay, and the T5 too would be the same value that's
Correct.
inside the subroutine.
Whatever's the
Okay,
most
so
recent change
Okay.
will be the
Okay,
yeah.
now makes sense. Sorry.
Okay.
It's just that
Yep.
confused me a little bit.
Okay, so this guy should ultimately do the same thing it did before, but we should have a 100 in T4 now. So I'll do a 7 this time. Oh, hold on. Oh, remember I said we have an infinite loop? I got to set it back because we're not jumping to RA. We want to jump to T2. T2 is the value I preserved. Okay, I preserved it here, jumped to do something, did something, jumped to where T2 is, which is the old value of RA. There's my 6. And so now T4 should have a 100 in it, proving we got to the do something. Here's T4 with the 100 in it. And then we're back in our T0 is 6, which is the number I typed in for my input. Make sense? Okay, so we do support subroutines inside of subroutines as long as we preserve the RA register.
Yeah, if we put in the
Otherwise,
All bets off.
all bets off. You start calling too many JALs, and RA gets overwritten 9 times. The last place you're going back to is that one. Or you better preserve, remember your home. Maybe, if you're an assembly programmer and you tend to make lots of mistakes early on, maybe there's an advantage of just like maybe storing in like T12, like the original value of your, like the beginning of your program, so you can get back home to at least line 1. Okay, so let's take 5 minutes and then we'll finish our last piece here. Yeah, because we won't have enough time otherwise. We could do 3 minutes.